Alright, it's lesson 9.4. And in this section, we're going to review 4 elementary power series that we've learned in our previous lessons. And yes, you are expected to know this from memory because there is no formula sheet on the AP Calculus exam. Okay? So yes, you should know these. And then we're also going to tackle something new called an alternating series. So, do you actually remember what these are from lesson 9.3? Well, if you don't, I'm so glad I'm here. Here they are. For sine x, this is the one where we had terms of x that were odd. Remember this? Hmm. Oh, maybe it's coming back to you now. Yes, yes, yes. And then we have the general term where we know that every second term is positive. So I have negative 1 to the power of n. And then I have this x to the power of 2n plus 1 all over 2n plus 1 with the factorial. And that's the general term. It allows you to write every single term. And then don't forget, it has to be an infinite series, so plus dot dot dot. Okay? And I think this was from example number 4 in lesson 9.3. Go ahead and double check. We also did cosine x, and that one was very similar to sine, except it was starting with 1. And then now we're also subtracting, so x squared over 2 factorial. Then we're adding x to the power of 4 over 4 factorial, then subtracting, and so on. And here we have the general term of negative 1 to the n, just x to the power of 2n, because all of our exponents are even, and we're dividing by 2n all in the factorial. And then don't forget plus dot dot dot. Okay? Then there was e to the x. And I don't know if you remember that one, but this is the one where the derivative is the same. So 1 plus x plus, x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. The general term here is just x to the power n over n factorial, and yes, once again, plus dot dot dot. And I think this was example number 1 from lesson 9.3. And then you have to go a little bit further back. I think it was lesson 9.2 to help us figure out natural log of x's elementary series. And this is the one where we had the factor of x minus 1. And then we have x minus 1 squared over 2. And then we had x minus 1 cubed over 3 with a plus sign now. And minus and so on and so forth. Dot dot dot. Plus the general term of x minus 1 to the power n. But because there is an alternating negative, positive, we're going to do this. Negative 1 to the n minus 1 term. I believe every second one is negative. And then don't forget we should divide by n. Okay? And then plus dot dot dot. Alright? And by the way, this one we had a restriction. Don't know if you remember, but this was only true if x was between 0 and I believe 2. Okay? Example number, I think 9 on page 198, which was lesson 9.2. Okay, so with these ones that I want you to know by heart, we can do things to them, like creating new ones. How do we create new ones? Just like how we created new power series with the geometric series, we can make substitutions, we can multiply them by things, we can do derivatives, we can do integrals, so it's the same thing here. Okay? So thinking about sine of x squared, right? So this one is really just replacing x with, you got it, x squared. So think back to what we had up here. There's the sine x term, and replace x with just x squared. So here we go. This is what you get. So the first term was x. It's no longer x, it's x squared. It used to be x cubed over 3 factorial, so now I'm saying x squared all cubed over 3 factorial, right? And then there's x squared to the power of 5 over 5 factorial. And then, yes, x squared to the power of 7 over 7 factorial. And if I were to continue this, don't forget, I can now rewrite the general term as, well, the negative 1 to the power n stays the same. Remember, all I did was replace x with x squared, so x squared to the power of 2n plus 1 all over 2n plus 1 all factorial. And then don't forget plus dot dot dot. Infinite series. Okay? And that's all you need to do. Okay? You can expand it out. You can, but leaving it at this I think is good too. Alright, so the next one, cosine root x. Yes, yes, yes. Think back to what cosine looks like. So here we go. 1 take away, it used to be x squared. Now it's root x all squared. Used to be x to the power of 4. Now it's root x to the power of 4. And so on and so forth, right? Dot, dot, dot. Don't forget plus, and it's negative 1 to the power of n. And it now be root x to the power of 2n all over 2n with factorial. Okay. Now for this one, I will simplify because I think it looks nicer if it does. That's just 1 minus what's root x squared. That's just x. Root x to the power of 4 is just x squared. And so on. And notice then this will be negative 1 to the power of n, and then root x to the power of 2n. Remember, root x is x to the 1/2. And multiply this by 2n, so you just get x to the n, which makes total sense because that's what all the other terms here say. And then all over 2n factorial, and then plus dot dot dot. Okay? Good. So for number 2, yes, I replaced x with root x. All right. Now with number 3, we're not doing any replacing, but what I see here is I'm taking the e to the x function and I'm multiplying it by x. So really I'm taking the e to the x function here in black and multiplying each of those terms by, that's right, x. So I'll write it out like this, x times, and it'd be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and once again the general term, x to the n over n factorial plus dot dot dot. And of course, if you want to expand this out or multiply this out, then x plus x squared plus now x cubed over 2 factorial plus x to the 4 over 3 factorial plus dot dot dot. And then now, instead of this x to the power of n, you have an extra x, so x to the power of n plus 1 over n factorial plus dot dot dot. And that is your new power series. Okay, now you're like, number 4, 1 over x, where did that come from? I don't see anything with 1 over x, but you do have ln, and what's the connection between ln and 1 over x? Yeah, I hope you remember that the derivative of the natural log of x gives you 1 over x. So really, I need you to take the derivative of the natural log function for the power series. So you're taking the derivative of, and I'm just going to copy this from above, x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3, and so on and so forth, right? Dot, 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 plus negative 1 to the power n minus 1 times x minus 1 to the n all over n plus dot dot dot. So go ahead and take the derivative, please. The derivative of the first term here. X minus 1. Well, that's just equal to, yep, 1. And then the derivative of the next term, I guess the 2 gets brought down to the front, 2 bracket x minus 1 over 2. You'll see the next one here is 3 bracket x minus 1 all squared over 3. And I'm thinking, I think you know what this is. N gets brought down to the front, x minus 1 to the power of n minus 1 over n. And then notice how, yes, these coefficients, goodbye, goodbye. So you're really just left with 1 minus x minus 1 plus x minus 1 all squared minus blah 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 plus negative 1 to the power n minus 1 times x minus 1 to the power of, yeah, you got it, n minus 1 plus dot 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 dot. I don't need a close bracket, I guess. Just go on forever and ever and ever. Okay, so once again, it's a nice power series. So guess what? We can just take the derivative of each of the terms. Now for number 5, guess what? I'm asking you now to do the integral of each of the terms. So, let me draw a line here so we can separate this. But yeah, it's the integral from 1 to t of, yeah, you got it, all those terms. Big bracket, x minus 1 minus x minus 1 squared over 2 plus x minus 1 all cubed over 3, and so on and so on and so forth, okay? And of course, I should have a dx here. I'm not going to worry about that general term yet. I'll do it later on. And then we're going to anti-differentiate this, right? So here we go. That'll be x minus 1 to the power of 2 divided by new exponent. The next one will be x minus 1 to the power of, add 1, that's right, 3, divide by the new exponent, so you have a 2 and a 3 now. And then here we got x minus 1 to the power of 4, divide by 4 and a 3 now, and so on and so on and so forth. And you're going to evaluate this whole thing from 1 to t, which means you're going to plug in t, so t minus 1 squared over 2, take away t minus 1 cubed over 2 times 3. That'd be t minus 1 to the power of 4, and then this is 3 times 4. And then I can give you the general term now, plus dot dot dot, plus, and think about what you've done. You've now kept the negative 1 to the n minus 1. You've replaced the x with the t, and you added 1 to the exponent. And then the denominator now is just n times that new exponent, n plus 1. And yes, this goes on plus dot 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 dot. And that's what you get for evaluating with t. Now, I should really plug in 1 as well, but what do you notice when I plug in 1? So it's this whole thing here minus me plugging in 1, and I'm not going to ask you to write the terms, but 1 minus 1 is, that's right, 0. These are all just going to be 0, 0, 0, 0, 0. So do I actually need to write that there? Probably not. They're all 0. So guess what? An answer like this would be perfectly fine. Okay, there you go. Done. So once again, once you've written it as a power series, you can do the derivative, you can do the integral, just use power rule. Okay, so the next thing I want to talk about here is something called an alternating series, and you've actually seen a whole bunch of these already. Because an alternating series is really a series whose terms alternate between positive and negative. It's all of those series where the general term has that negative 1 to the power of something, right? And we've seen 3 of them already. Let me look back up here. Do you see 3 of them with the negative 1s? So look, positive, negative, positive. Look, positive, negative, positive, right? Look, positive, negative, positive. Elementary series that are alternating. Right? Now, what's so nice about these alternating series is we can actually have a test that allows us to determine if that series actually converges. What does this word converges mean? It means that the sum actually becomes a finite number. It's no longer an infinite sum. Interesting, eh? So what they're saying is this. For an alternating series, and these are the two examples, okay, negative 1 to the power n, so that's like the first term is negative, the second term is not, so on. Or this one here, the first term is positive, the second term is not, vice versa, right? Still alternating. What you'll see is that yes, the terms always alternate. And if you have this criteria here, where the next term, the nth plus 1 term, is always less than or equal to the current term, okay? For all n after a certain n. So we're not saying it has to be like that at the beginning of the sequence, but way down when we're talking about the 100th term or 11th term, sorry, not the 11th term, the 100th and first term and so on. Yeah, those have to be following this restriction. The idea, of course, being that the terms never increase in absolute value. Okay, so pretty much your idea is it's decreasing or equal to. And the third criteria is if I were to take the limit as n approach to infinity of the general term, that's a sub n, we would expect that this equals to 0. Okay, because that means that when n is really large, the number is so small that you're pretty much adding nothing to it, and that's why your series actually becomes finite. So if you have all three of these conditions, then you can say that the alternating series converges. Okay? So let's take a look at these two examples, see if they actually converge or diverge. What's diverging? Oh yeah, the sum goes to infinity. Now, it might be nice for you just to write out the first few terms if you can't see what this looks like, or think about it in your head. If I plugged in n equals to 1, 1 plus 1 is 2, so negative 1 squared is a positive number, so I'm thinking this is now positive 1. I know that this will alternate, so for the next one it must be negative, and then I think it's just 1 over 2. Then we'll alternate again, 1 over 3, 1 over 4, and so on. Okay, so this is my series. Starting at 1, then subtract half, then add 1/3, 1/4. You see it goes back and forth, back and forth. So first of all, do I have the first one? Do I have the terms that are alternating? Alternating terms? Yeah, check. Number 2, are the terms decreasing? So if I look at the next term, n plus 1 term, and I compare it to the current term, 1 over n, is it decreasing? Is it less? You bet. So this is decreasing. Good. And once again, I don't worry about the absolute value sign. I'm just looking at the terms, and they never increase in absolute value. So we know this one always decreases. So that's good. And the third thing now is I need to check this. Does the limit as n approach to infinity of the expression 1 over n equal to 0? And if I take this and plug in infinity, you bet this also equals to 0. Okay? So I've satisfied all three of these conditions. I can then say by the alternating series test. And by the way, yes, there's a short form for this, AST. This series, or if we really want to be more specific, just write out what it is, right? The sum of n equals to 1 to infinity, negative 1 to the power n plus 1 times 1 over n is convergent, or just convergence. Okay, just say convergence. I think that's easy. Cool. Okay, so once again, if you can't see it right away, don't worry. Write out the first few terms, and then go through the three-step process, and then tell me if this series converges or diverges. So, you try number 7 yourself, and let's see what you get. Okay. You know what I say. Press pause. Yes, press pause in the video. Try yourself first, and come back. First term, positive. 1 plus 1 is 2. 2 over 1 is 2. Let's do 2. That's minus now 3 over 2. And then 4 over 3. And then 5 over 4. And then blah, blah, blah. So alternating terms, you bet. Decreasing. So is n plus 2 over n plus 1 less than n plus 1 over n? Yeah, I think so. Look at these two. This is like 1.5. This is like 1.3 repeating. This is like 1.25. So yeah, check. Decreasing. That looks good. And then finally, I'm going to ask you to take the limit as n approaches to infinity of n plus 1 over n. And in this case, I'm thinking, uh-oh, with the n behavior model, I can now just ignore the 1 on the numerator because n dominates, and this actually equals to 1. Uh-oh. So this does not equal to 0. Uh-oh. So we know this can't converge, but do we know if this diverges? And this is where I'm thinking, can you go back to what you've learned a long, long time ago? Maybe not that long, but a few lessons ago. Because remember this test called the nth term test for divergence? If the limit as you take n approach to infinity of the term does not equal 0, then we can show that it diverges. So going back to the example, I wouldn't quote the alternating series test because it didn't satisfy the conditions, so don't quote that one. But what I can say now is by the nth term test, the series n equals to 1 to infinity of negative 1 to the power n plus 1 times n plus 1 over n diverges. Okay? Don't quote AST here because AST, the alternating series test, can only be used to show if something converges. Okay? Once I had this statement here that the limit was not equal to 0, I now flip it over to the nth term test, and that is my rationale and reason why this diverges. Okay? So now ultimately we have three different tests for this idea of convergence or divergence. Now, be careful though, the first one, the nth term test, is only used for diverging, okay? Only for divergence. Okay? I can't show it converges. Okay? It's the geometric series test where you can show converging and diverging. Okay? And the key is to look at the ratio, right? The common ratio. If r is greater or equal to 1, diverges. If the absolute value of that is less than 1, it converges, and it also has that formula to help you figure out what it is equal to. And then now we learned today that the alternating series test is only for convergence. Okay? Can't tell us if it diverges, but if those three statements are true, then we can say by the alternating series test it converges. All right? So that's it for 9.4. Okay? Our next lesson will tackle a little bit something a little bit different, yet still build on this idea of alternating series. So once again, please work on the assignments so that you can have a good understanding of this topic before you learn the next thing in the series. Get it? In the series. See you then.